Hello everyone, welcome you all to week 9 problem solving session for the course Introduction to Group Theory. I'm the NPTEL PMRF teaching assistant for the course. I'm Priyanka Sharma. I'm a research scholar from the Department of Mathematics IIT Patna. In today's session, we will discuss more about group actions and their applications. So, first of all, I want to recall what is a group action. So, whenever we discuss about group action, what we need? We need a group G and a non-empty set, say X. Then we say that G acts on X if we have a group homomorphism from G to the permutation group of X. Uh, we say we denote it by like equivalently we can do this like G cross X to X, and we denote it like uh, G dot X. This is mapped onto Gx. Okay, then this will satisfy two conditions. First one is if we use the identity one like Ex, like in place of G we take the identity element, then this will be mapped onto X. And second one, suppose we have two elements G1 and G2 in G, and we do this G1, this will be at after this G2, it's on X. So this will be same as like G1 of G2 of G1 dot G2 dot X. For all G1 and G2 belongs to G, and for all X belongs to X. So if this satisfies, then we say that G acts on the set X. Now we discuss about the class equation, which is an important application of this group action. So whenever we use the conjugation as the group action, we get the class equation. How to do this? So suppose we have a group G, and this G acts on G itself, that is G and the non-empty set X, they both are same. And G acts on itself via conjugation action, that is the group action is the conjugation. We denote it by this. C, this is from G to SG, and this is defined by this, like G is mapped onto CG, where this CG is a map. It's this is a bijection from G to G, and this map every element X in G by GX G inverse, where this G is coming from G, and this is the element which is using to define the action. Okay, so this thing X is mapped onto GXG inverse. So this GXG inverse, this is the conjugate of X in G with respect to the element G belongs to G. So we are defining the group action using this conjugation. So this is the conjugation action. And under this, the group G or any group G will act on itself. Now, what is the center of G? So center of G, this is the collection of all those elements of G which commutes with every element X belongs to G. And this is indeed a subgroup, actually the normal subgroup. Now, how we define the centralizer of any element X in G? So, for a fix X belongs to G, the centralizer of X in G, which is denoted by CG of X, this is the set of all G belongs to G such that Gx is same as Xg. Okay, that is the elements of G which are centralizing the given fixed element X in G. Now we can see that the center of G is the intersection of all the centralizer of G, where this intersection is taking over the elements of G. Now, what is the fixed point set? So whenever we have a group acting on some set via a group action, we can define some terms like uh, fixed point set, orbit, stabilizer, and kernel. So first one, what is fixed point set, which is denoted by xg, but here x is g itself, so this will be g actually. So this will be those elements of x for which Cg of x is x. Actually, this is, we know that xg is the set of all those elements of x, or this is a subset of x such that g dot x is x for all g belongs to the acting group G. Okay, and here this g dot x, that is the group action, this is defined by Cg. Okay, so thus we will get uh, this condition Cg of x must be x. And what is Cg of x? This is gx g inverse. So as G is a group, thus this will be equivalent to this Gx equals to Xg. So Gx equals to Xg for all G belongs to G. So collection of uh, all those elements of X, this will give us actually center of G. That is the fixed point set of any group under the conjugation action. This will be the center of the group. Now, what is the orbit? So, orbit is again a subset of the given set X on which the group is acting. So, orbit of X, this will be G dot X. That is, whenever we apply the group action on this given element X in X by each element of G, and if we collect those, we will get the orbit. So, here this G belongs to G. Okay. So again, this g dot x, this is cg of x, that is the conjugation of x. So cg of x, this will be gx g inverse. So whenever we collect this gx g inverse for any element x, we will get the conjugacy classes of x in G. So what is the orbit? Orbit of x is the conjugacy class of x. Okay. So actually the orbits are conjugacy classes. If we act, if a group is acting on itself under conjugacy action. Now what is the stabilizer of any group element? So stabilizer of X, this is denoted by Gx, and we note that stabilizer is actually a subgroup of the acting group. So here this will be g of x, this is actually g belongs to g such that g dot x is x again. It means gx under the conjugation action, this will be cg of x, this should be x. So this will be again cg. And what is cg? Cg is defined by this, the centralizer of x in G. Now, what will be the kernel of C? What is this C here? C is the group action. So, kernel of this group homomorphism, this will be the center. Now, what will be the form of orbit decomposition theorem? So, what is the orbit decomposition theorem? Uh, Suppose we have a group G acting on some non-empty set X, then this expression is the orbit decomposition theorem. That is the cardinality of the non-empty set X, that will be the cardinality of Xg plus summation of cardinality of G divided by cardinality of Gx, where this summation is taking over X, and this X belongs to lambda 1. So this will be reduced into this expression, that is the cardinality of G, or the order of the group G, because this time X is G itself. This will be like the first term in RHS, that will be the cardinality of xg. Now, what is the cardinality of xg? What is the cardinality of fixed point set? That is the uh, cardinality or the order of the center actually. So the first term will be order of the center plus summation x belongs to lambda 1, cardinality of g divided by cardinality of gx. And what is gx for a given x in G? This is Cg of x. Okay, this we have seen here. Okay. This one. So the class equation will be cardinality of G is, or the order of a group is the order of the center plus summation of these terms. Here, this lambda 1, this is actually the subset of x, and this will consist of all those x belongs to x such that the cardinality of CGx this is less than the cardinality of G. If they are equal, then we will get the lambda naught, and that will contribute in the first term. Okay. So if G is a P group, what is the meaning of a P group? P group means the order of the group is P to the power n, where this P is a prime number and this n is a natural number. So if G is a P group, then the order of the center of G that is greater than or equal to P. So either this will be P or this will be something greater than P, and that will be actually some P to the power I, because this ZG, this is a subgroup of G, and if order of G which is given as a finite number, so by Lagrange's theorem, the order of ZG, this will divide the order of G. So this will be actually P to the power some I, where this I can be something between 1 to n. That is, if G is a P group, then its center, that will be non-trivial. And if order of G is P square, then G is an abelian group. Now, what if the order of G is P to the power n? So we can say that G acts on some set X, then the cardinality of X, that will be the that will be equivalent to the cardinality of G under modulo P. This is obvious from the orbit decomposition theorem. Okay, because if we use the conjugacy action here, then what we will get here, like this will be some like order of G that is P to the power n. If this will be some P to the power I, so this will be some like P power. And if we take modulo P, then this will be 0, and cardinality of X and the cardinality of XG, they will be same. Now we have an important theorem in group action. Whenever we want to find the possible orders for elements of a group, and for the further extension, if you want to know the order of subgroups in a group, then the theorem is useful. This is Cauchy's theorem, and this can be proved using group action. So what is the statement? Suppose we have a group G, which is a finite group, and P be a prime number such that P divides order of G, then there exists an element of G of order P. So, see, the Cauchy's theorem, this is given for a finite group. This is the initial assumption. And here we are taking that for a given number, if the number is dividing the order of group, then there will be an element of that number. But this is true if we have the number as a prime. If the number is not prime, if that is a composite number, then we can't say that is the converse can be true, cannot be. We can have some counter examples for that. But if we have a prime number, then for sure there will be an element of order that prime. Now again, using group action, we can prove this result, which we have earlier discussed. So suppose we have a group G and H and K, they are two subgroups of G. And if HK, that is the product of H and K, this is a subgroup. So yeah, this is not always a subgroup. If H and K commutes, then we can have their surety. So what will be the order of this group HK? So the order of HK, this will be the order of H multiplied by order of K divided by order of H intersection K. So as H and K, they are subgroups of a group G, then their intersection, that is H intersection K, that will again be a subgroup of G. So we have this result. Now, how we can prove this using group action? So this is a hint. So actually this HK, this is a group and we need a set. So this time we suppose that the group G for which H and K are subgroups, this is the non-empty set. So we want to define group action. So we need two things, group and a set. So HK, this is a group and G is a set. And now we suppose that this group HK, this is acting on a non-empty set, that is the group G, via the group action. This is the group action actually. So to define group action, we need some group element here and here we need some element of the given set. So HK is the group whose elements are of the form HK, we can say, or like HK directly. So if we write H cross K, then we can consider this. Okay, so that's why we are using this notation. So HK dot G, here this dot is the representation of the group action. Okay, so H comma K dot G, this will be this like somehow double-sided conjugation. So the group action is defined by this H G K inverse. So if we use this group action, then we can prove this result. Now, what are G sets and morphisms on them? So, let G be a group and X be a non-empty set. Suppose G acts on the set X via some group action tau, then X is called a G set. So a set will be a G set if we have a group action by which the group G is acting on it. So in this case, we say that X is a G set. Now, we have a term called transitive action. So what is a transitive action? This is a special type of group action. Group action we have already discussed. So when will we call a group action as a transitive action? So suppose we have a group G which is acting on X, then we say that G acts transitively on X if for all X and Y belongs to X, there exists some G belongs to G such that G dot X is Y. That is for any given pair X and Y in the set X, we can always have an element of the group by which we can form, like we can find the another element. So suppose we start from one element, say X, then we get an element from the group G. Whenever that element acts on the element X, we will get the another element Y belongs to X. So this is equivalently saying that there is one and only one orbit. So we say that a group action is transitive if we have only one orbit for that group action. Now, what is an example for this? So suppose we have a group G and we have a subgroup, say H of the group G, and this G, this is acting on this quotient group G mod H via the group action defined by this, that is G dot AH. This is GAH. Then the orbit of H, this will be G dot H, which is GH. So this set of all GH, this will give us actually G mod H. Okay, that is the set itself. So in this case, we get something like this. Orbit of X is the set X itself. Okay. So whenever we have this, we say that the group action is transitive. Now, what is morphism in the sense of group action? So suppose we have two G sets, X and Y. What does it mean that X and Y, these are two G sets? It means that the group G is acting on X via some group action, say tau, and G is acting on the set Y via some another group action, say tau dash. So this is the thing actually. Tau, this is a group homomorphism from G to Sx, that is the permutation group of X, and this is defined as G. Mm, this is mapped on tau of G, where this tau of G, this is a bijection from X to X. And tau dash, this is defined from G to Sy, where this Sy is the permutation group of Y. And this maps every G to tau G, tau dash G, where this tau dash G, this is again a bijection, but on the set Y. So this is our assumption, that is X and Y. These are two different G sets. Then a map, say F from X to Y, this is said to be a morphism if we have these conditions. That is F of G dot X, this is same as G dot F of X. And this should be true for all G belongs to G and X belongs to X. Okay. So see, actually, this is coming from G cross X to X, right? So this G dot X, this will be an element of X, and F is working on X. So this is something like F of X. Okay. So F of G dot X, this will be same as G dot F of X. So yeah, uh, F of X, that will be an element of Y. So this will be G dot some Y. Where this element coming from the another set Y. So this G, this is an element of the group G, and this is used here to define group action on elements of both the sets X and Y. Okay, so if the assumption or if this condition is true for all the group elements and for all the elements of X, then we say that the map F is a morphism from X to Y. Now, how we can pictorially represent the morphism? So this is a representation. So X and Y, these are again two G sets, and F, this is the map which is defined from X to Y, which is mapping every X to F of Y. And again, uh, X and Y, they are two G sets. So whenever we define the group action, we will have some group homomorphism, which will give us the bijections tau G and tau G dash with respect to the corresponding permutation groups actually. So from X to X, we have some tau G, and from Y to Y, we have some tau dash G. This tau G, this will map every X to tau G of X, and this is actually G dot X if we use the group action. And tau dash G, this will map this f of x, that is the image of this element x under f, uh, into this tau onto this tau dash G of f of x. So this will be the same element G dot f of x. Okay. Why? Because this tau G dash, this is a bijection from Y to Y, and we have a group action. So this G dot f of x, that is G dot some element of Y. So this is the group action on Y. Okay. So okay, this will be erased. This condition, this condition is actually the commutativity of this diagram. So the map F will be a morphism if this diagram commutes. What does this mean? It means that if we start from this X, so under this F, we will get this X to f of x, and then G dot f of x. And if we go in another way, then X will be mapped onto tau G of x or G dot x, and this will be mapped onto f of tau G of x. Okay, now an example of morphism. So uh, suppose G is a set and it acts transitively on some non-empty set X. We fix an element X belongs to X, then what will be the orbit? Orbit will be the entire set X. And the stabilizer of this fixed element X naught in G, this will be the set of all G belongs to G such that G dot X naught, this will be X naught, and this is a subgroup of G. Now we define a map F from G mod Gx naught to orbit of X naught uh, by this definition. So G mod G naught, this group will have elements of the form G capital G X naught, and these kind of elements will be mapped onto G dot X naught. So this is a bijection, and this is a bijection between two G sets. This G mod Gx naught and orbit of X naught. These are two G sets. That is the group G um acts on these two sets, and this is the corresponding diagram. That is, this is G mod Gx naught, and this is X. So again, we can see that this diagram is commutative. Thus, this map F, which is defined from G mod Gx naught to orbit of X naught, this is a morphism. Now, if we have a bijective morphism, mm, then what will be the consequences? So to define a morphism, first we need two G sets, say X and Y. They are two G sets, and we have a morphism F from X to Y. And we want to define the inverse of the morphism. So For the existence of inverse, first we need to confirm that the map is bijective. So that's why we are assuming that f from x to y, this is a bijective morphism. So if f is bijective morphism, then f inverse, that is the inverse of the morphism f, that uh, that will exist, and that will again be a morphism of G sets. And F inverse, this will be a morphism defined from Y to X. Now we have some examples on group actions. So let G be a finite group, and we have a positive integer k, which lies between 1 and the order of G. Then with respect to this number k, we define this sigma k as a set of uh, the set of all those sets of the group G who has the cardinality as the number k. Okay, that is the sigma k is a collection of all those subsets of G which has order k, which has k number of elements, we can say. So under this assumption, that is a finite group G, and with this notation sigma k, we can define some group action. So G acts on this set sigma k via left multiplication. So this is a group action, that is G dot x. This is the way to define a group action. So G dot x is defined as this GS, where S is coming from S. So that is G dot S. This is same as GS. See, actually, this S is a subset of G. So S will have elements of the group G itself. So that's why this GS, this is like well defined. Okay, well defined under the group operation itself. Okay, so here this dot is actually the notation of group action, but here we are removing it because this is this will be reduced in the group operation itself. Okay. So we can uh, check that this map S to GS, this is a bijection. So as this is a bijection, what we can see, uh, what will be the orbit, what will be uh, this stabilizer for this group action. Let's see. So actually G is, let me use another color. G, this is acting on the sigma k. Okay. And we pick an element S in this set sigma k. So we define order of this element. So order of S, that will be G dot S, and that is same as GS. So what is GS? GS, where this G is varying over the group G. So this will be this quotient group G mod S, and this is a subset of this sigma k. Now, what is the stabilizer of S with respect to this group action? So stabilizer of X, where this X is an element of sigma k. So this will be the uh, subset consisting of all those group elements which stabilizes the element S, that is G dot S or GS. This is same as S. So this GS, this is indeed S, okay, because this thing actually give as G belongs to S, okay. Hmm. Now we can see this. Uh, This is the orbit decomposition theorem. That is the cardinality of the set of orbits, uh, which is cardinality of G mod S. This is the cardinality of the group divided by the cardinality of GS. So this will give as this cardinality of G mod S is cardinality of G divided by the cardinality of S. So this is the form of Lagrange's theorem actually. Okay. Now, in the first example, we choose the left multiplication as the group action. Now, in the second example, we are changing the group action with this conjugation. So this time G dot S, this is defined by this conjugation, which is G S G inverse, which is obviously the set of these type of elements, G S G inverse, where this S is coming from S. So again, we can see that the map which maps S onto G S G inverse, this is the bijection. So for this group action, we can again define the orbit stabilizer and the orbit decomposition theorem. And let's check what that will give. So what will be the orbit of S? So orbit of S is the set of GSG inverse, where G is coming from the group G. So this GSG inverse, this is actually the conjugates of S in G. So orbit of S is the set of all conjugates of S in G. Okay. Secondly, what is the stabilizer of S in G? So this will be the subgroup of all those subgroup having all those group elements for which G dot S is S. That is G S G inverse is S. So this will give us the normalizer of um, the subgroup S in G. And the orbit decomposition theorem that will have this form, that is the cardinality of orbit, the group of orbit of S, that will be the cardinality of G divided by the cardinality of GS. That is the number of conjugates of S in G. That will be the number of conjugates. Okay, that will be the order of the group divided by the order of the normalizer of S. In the next example, we are actually modifying uh, this notation. So in sigma k, we have the set of all subsets of G. If we have the set of all subgroups of G having order k, then we have the notation Ck. So we can again define a group action under the conjugation. Okay. Now this is an interesting example of group action in graph theory actually. So suppose we have a graph G, it has 8 vertices, 1 to 8. This V of G, this is the set of vertices, and E of G, this is the set of edges of the graph G. And we define automorphism of G, that is the automorphism of the graph. So what it will be? It will be the map uh, from S8, that is the permutation group of order 8. And how we define this? So sigma of Eij, that is sigma image of the edge joining vertices I and J. This will be the edge joining vertices sigma I and sigma J. So the sigma is an element of S8. So obviously we can define sigma I and sigma j for all I and j between 1 and 8. So sigma map sigma actually transforms each edge of this graph. And how? uh, by transforming the vertices of that edge. Okay. So this the group of all automorphism of the graph G. This is actually a group. So uh, for this group, we can define a group action. So yeah, automorphism of G, this forms a group under the composition, because here we are taking maps actually. So the group operation will be the composition of maps, and this group acts on the set of vertices. And we can also check that uh, the group action is transitive. Now, the Burnside lemma. So this lemma is useful uh, to get a connection between um, X, G, and G. So suppose we have a finite group, so that we can talk about the order of G. So if G is a finite group and this is acting on a non-empty finite set X, then the set of X mod G, this will be 1 by the order of G into summation of cardinality of XG, where this summation is taking over G belongs to G. Now, what is this XG? XG is a set of X uh, like this. This will contain all those elements of X for which G dot X is X. Okay. So, this is the theory part. For further details, you can refer the lecture videos where you can get all the proofs and like some details for this discussion. Now we come to problems. This is our first question. So, okay, let X is the set consisting of 1, 2, and 3, and G, this is a group S3, that is the symmetry group S3. Define a map star from G cross X to X, that is, this is something like group action form, such that sigma star A is sigma of A. Then the question is, show that this star is a group action. And further, find all stabilizers and orbit with respect to this group action and check that um, the action is transitive or not. Okay, so let's solve it. So the given non-empty set is X, 1, 2, 3, and group G is S3. That is the group of all permutations from this set 1, 2, 3 onto this set itself. And define a map star from G cross S to X by sigma star A is sigma of A. So we need to check whether this is a group action or not. So let's check the first condition. ID star A. Actually, this is the identity of S3. That is the identity map. This will be identity of A. This will be A for all A belongs to X. Okay, so this is the first condition, which is true. Secondly, uh, let sigma 1 and sigma 2, these are two elements of the group G, that is S3. That is sigma 1 and sigma 2 are two permutations from S3. Now, what is sigma 1 star sigma 2 star A? A is an element of X. So this will be sigma 1 star, this is sigma 2 of A, which is sigma 1 of sigma 2 of A, or it can be written as sigma 1 sigma 2 A. And this is true for all A belongs to X, and also we took sigma 1 and sigma 2 from G arbitrarily. So this star is a group action. Now the next part, find all stabilizers for this group action. So stabilizer of 1 belongs to X. That is stabilizer in G, or say S3 of 1, or alternatively we can say S3 of 1. Actually, this must be in subscript, and that will create some confusion. So that's why I prefer to use this notation this time. What will be this? This will be all those sigma belongs to G, that is S3, such that sigma star 1 is 1. Okay. It means the set of all sigma such that sigma of 1 is 1. That is, we need all those permutations on X which maps 1 to itself. So we can have, okay, see, this is X to X. We have these three elements 1, 2, 3, and what we need, 1 is mapped onto itself. Now, there is no restriction on the images of 2 and 3 this time. So image of 2 can be either 2 or 3, and image of 3 can be either 3 or 2. So if we have this thing, then obviously this sigma will be the identity map, and this one. So here this one is fixed, 2 is mapped on 3, and 3 is mapped on 2. So this will be same as writing 2 3 or 3 2 as a cycle. Okay. So this will be the set of these two elements, identity and 2 3. Okay. Similarly, what will be the stabilizer in S3 of 2? So this will fix 2 onto itself. Images of 1 and 3, they may be same as 1 and 3, or they can be like swapped. Okay, so this will be the identity and 1 3, and the stabilizer of 3, this will again have 3 elements. Okay. So stabilizer part is also done. Now we need to find the orbit. Okay. Now what happened in if we check the orbit decomposition theorem? Okay. So for 1 belongs to X, cardinality of orbit of 1, that will be cardinality of G divided by the stabilizer of 1 in S3. Okay, that is 6, which is actually the cardinality of S3. Okay, so this is 6 by 2, that is 3. Okay, it means the orbit of 1 that will have 3 elements. And orbit of 1, this is a subset of X. Okay, and X itself has 3 elements. So obviously the orbit will have those 3 elements. Therefore, orbit of 1 is X. Obviously, orbit of 2 and orbit of 3, they are X. So how many orbits are there? There is only one orbit, and that is the set X itself. Okay. Therefore, there is only one orbit which is X. Okay. Is the action transitive? So, yes, this is the condition for an action to be transitive. So, as there is just one orbit, so we can conclude this also. The action star is transitive. Okay. Okay. Now come to second question. Suppose G is a group and this acts on two sets S and T, then show that this this notation, this map star defined by this G star S comma T as GS comma GT is a group action on S cross T. Okay, so S and T, these are two sets on which this group G is acting. Actually, we can say that uh, S and T be two G sets. Okay, so whenever we have two G sets, we can define another G set, which is the product, the Cartesian product of those G sets. Okay, so define S cross T, that is the product of the sets S and T, and this will have these elements S comma T, where S is coming from S and T is coming from the set T. Okay. So we are to prove that S cross T is also a G set. Okay, so if this is a G set, then obviously the group G is acting on S cross T. That is, we need to find a group action this time. Okay, so what will be the group action? So the group action is defined by the map star, and this is the definition of the map. Okay, and under this definition, we'll prove that ST is a G set. So let's do it. And define a map star from G cross S cross T to S cross T by G star S comma T is GS comma GT. Okay. Or S comma T belongs to S cross T. See, here this thing actually, GS and GT. How we define this? So actually, I would like to write it as G dot S and G dot T. So as the group G is acting on S and T, so here we are using that group actions. Okay. So let's check. If E belongs to G is the identity, then what will be E star S comma T? That will be E dot S comma E dot T, and as S and T are G sets, so this will be S and this will be T. So this is the first one, and second condition. Uh, now we need two elements from the group G1 and G2 belongs to G. See that G1 star G2 star S comma T, for some S comma T belongs to S cross T. This will be G1 star G1 dot S G2 dot S. Okay. So this will be G1 G1 dot G. Okay, this will be G2. G2 dot S. Sorry, this will be T. Comma G1 dot G2 dot T. Okay. So this will be G1 G2, that is the composition, dot S comma G1 G2 dot T. Why we can write this? Because again, capital S and capital T, they are G sets. So we will have group actions, which is dot here. Okay. Thus, we can conclude that star is a group action, or S cross T is a G set. Okay. Now, what is the stabilizer of uh, some element ST from this G set S cross T? So the claim is that the stabilizer of S comma T is the intersection of the stabilizers of S and T. Okay, let's do it. Mm, I would prefer to use this notation. Stabilizer in G of this some element S comma T. This will be the subgroup consisting of all those G belongs to G such that G star S comma T is same as S comma T. By the definition of star, we will get that G dot S comma G dot T, this is S comma T. That is the stabilizer of ST. This will be the subgroup having all those group elements such that G dot S is S and uh, G dot T is T. So the first condition, that is G dot S is S. Uh, so this will give us like all those G belongs to G, which are in stabilizer of S, and G dot S is sorry G dot T is T. So if we collect all those G in G, then we will get the stabilizer of T in G. Okay. So we need G belongs to G such that this G is in stabilizer of S as well as in stabilizer of T. Okay. It means it will be in the intersection of the stabilizers of S and T. So stabilizer of S comma T, this will be the stabilizer of S intersection stabilizer of T. Obviously, here we are taking intersection uh, of subgroups actually. Now, come to the next question. There exists a non-abelian group of order 27. Is the statement true or false? So, let G be a group such that the order of group is 27. If we write it as prime factorization, we'll get 3Q. Okay, that is this G is a P group, or we can say 3 group here. Okay, for the prime 3. Now, we need to check the existence of non-abelian group. Okay, so what if we have an abelian group? If the statement of if we have a statement for that, so yeah, obviously we will have an abelian group of any given order, or like for um, any given natural number at the power. Okay, as the order. So what if G is abelian? Then there will be okay, we can say then G can be isomorphic to Z27, okay, or Z mod 27Z. Okay. Yeah, obviously there can be another abelian groups of order like PM, but for the assurance of existence in case of abelian group, we can have this. Now, what if G is non-abelian? Consider this group. G is the collection of matrices of this form 1AB 01C 001, where A, B, and C, these are coming from Z3, or say this Z mod 3Z. Okay, both the groups are isomorphic. Okay. So we can check that G is non-abelian. Okay, because we are having 3 by 3 matrices, and matrix multiplication is in general non-commutative. So yeah, we can have some examples for that. So we can choose A, B, and C, like such that we can have two matrices which are non-commutative. So you can check this. Now, what about the order of this group? So see, in this group, diagonal elements are fixed. Okay, and these elements which are in the lower triangulation, or we can say which are uh, below the diagonal, so they are 0. 1 and 0, they are in S3. So these 1, 2, 3, 4, 5, and 6, these 6 elements are fixed. Now A, B, and C, that is these 3 elements can be chosen in S3. Okay, so what will be the order of G? The order of G will be uh, the sum of number of ways we can pick A in S3, and number of ways we can pick B in S3, and number of ways in which we can pick C in S3. Okay, that is 3 by 3 by 3, or 27. Okay, so that's why the statement is true. Now come to the next question. Which of the followings can be class equations for a group? Okay, so some kind of equations are given, and we need to check which can be possible class equation for some suitable groups. Okay, so okay, first recall what is class equation. Okay, so see this. The orbit decomposition theorem, when a group acts on itself under the conjugation group action, we will get the reduction in class equation. Okay, so this is the class equation. That is, the order of group is the sum of order of center and summation uh, order of G divided by cardinality of the CG of X. Yeah, this can be order. Okay. So let's do it. Class equation for a finite group. Okay. Because we are defining the order of G divided by the order of CG of X. Okay. Hmm. Uh, Here, center of G is a subgroup of G. So, by Lagrange's theorem, order of center of G, this will divide order of G. Okay. And this is what we will have always. Now, actually, I want to connect it with some another questions also. Okay, fine. I will make another question for that. Okay, so let's talk about the first possibility. 1 plus 1 plus 1 plus 2 plus 5, which is 10. That is if possible, like if this equation can be a class equation, then it can be for a group of order 10. Okay. Now, what does this once uh, represent? Okay, so they are with respect to the center. Okay, like this can be summation order of G such that this is CG of okay, not X. This should be X. And if we take X belongs to lambda naught, okay, That is when these two terms, that is the order of G and the order of this stabilizers of X, if they are same, uh, for those X, uh, like they will contribute in this summation. Okay, so for that, actually this will be this ratio will be 1, right? So this will be summation 1 where this is taking for X belongs to lambda naught. Okay, it means in a class equation or in an equation which is being claimed to be a class equation, one will appear uh, and how many times? The repetition of one, that will be the order of the center of G. Okay. So it means the center of G is 3. But can it be possible? No, as 3 doesn't divide 10. So uh, it contradicts to the Lagrange's theorem. Therefore, it cannot be a class equation. Okay. Second part, 1 plus 1 plus 2. Okay. It means we are discussing about a group of order 4. If such a group exists. Okay. Because in the first option, actually no such group can exist. It means center of G, this is 2. This 1 plus 1. Okay. So actually, the Lagrange's theorem satisfies, but know that all groups of order 4 are abelian. Okay, because if we have a group G which has order 4, then it can have two choices up to isomorphisms. First, Z mod 4Z, and the second one is Z mod 2Z cross Z mod 2Z. Okay. First one is cyclic, second one is non-cyclic, but both are abelian. And if G is abelian group of order 4, then order of the center, that will be 4, as the group will be the center. Therefore, it cannot be a class equation again. Third one, 1 plus 1 plus 1 plus 1. That is a group of order 4s whose center has 4 elements. Therefore, G is isomorphic to Z mod 4Z. Okay. So yeah, we can say it is a class equation. Fourth example, 1 plus 1 plus 3 plus 3. This is 8. And order of center of G, that is 2, which is less than the order of G. Therefore, G is non-abelian, first of all. Okay. So, G is a non-abelian, of order 8, then up to isomorphism, G can be either D4 or D8 and Q4. Now come to the class equation again. What we have here? Um, the first term is order of ZG, and the second one is summation of G divided by the centralizers of X. And here we have 3 and 3. It means the centralizers or like this ratio, they must be 3, and the group is of order 4, order 8, either like GX or CGX, whatever you want to write here. That is 3. That is this is 8, right? So obviously, like we will get a contradiction here only. Okay, so yeah, this is a contradiction. Okay, because for this we cannot have a natural number. For more details, we can check the conjugacy classes in D4 and Q4. And one more thing. Um, okay. Okay, so we can consider at least this in detail. Fine. So yeah, this cannot be a class equation. Hmm. Next one. If G is a group of order P square where P is a prime, then G is abelian. So yeah, we have already discussed this. Order of G is P square where P is prime. Then what about the center of G. This will divide P square. So this will be either 1 or P or P square. So we have seen a theorem that if we have a P group, that is a prime power group, then the center will be non-trivial. That is, the order of ZG cannot be 1, or like this is greater than or equal to P. Now, what if the order of center of G is P? So, as the center is a normal subgroup, we can define Z mod G mod ZG. Order of this will be order of G divided by order of center of G, that is P square by P, which is P, which is a prime. It means this group G mod ZG, this is a group of prime order. Okay, it means G mod ZG is cyclic, but that will imply that G is abelian. Okay, and if G is abelian, then order of G will be same as order of center of G, or G and ZG, they are same. So yeah, this will be P square. Okay, so there can be only one choice, that is this one. And for that, G is abelian. Now consider this question. Find classes, conjugacy classes and class equation for Q4. What is Q4? This is the quaternion group. Okay, let me write them separately. 1 minus 1, I minus I, J minus J, K and minus K. If I write the elements, and we know that I dot J is K and J dot I is minus K, and so on. Okay. We are also aware about the orders here. And in the previous problem solving sessions, we have found the order of Q4. So we know that, uh, order of elements of Q4 and center of Q4. So Z of Q4, that has two elements, 1 and minus 1. Because we can see from here only that I and J, they won't commute. Similarly, J and K and K and I, they don't commute with each other. So we have only two elements in center, 1 and minus 1. It means the class equation will be something like 1 plus 1 plus something, some numbers greater than 1. So that is that can be seen mm, up to this. Now we need to find the conjugacy classes also. So conjugacy class of I, what will be that? That will be GI G inverse such that G belongs to G, which is Q4. Okay, so this will have Suppose we are taking G as identity, that is G as 1, then we get I. If we take G as -1, what we get? -1, I -1. Okay. And -1 is in center and -1 has order 2. So this will again give us I. Okay. So for these two group elements, 1 and -1, what we will get? We will get I itself. Now, what for G is I? We will get I, and here we will have I inverse. What is the inverse of I? That is -I. Now this is I, and I into -I, that will be -I square, that is 1. Or we can simply write it as I inverse. So this will be the identity and we will get I again. If we take G as -I, we will get I and -I inverse. So from here also again we will get I. What if we take G as J? Then J inverse means -J. So Ji, this will give us K, sorry, -K, and -J means this will be Kj, and that will be -I. Okay, so we will have another element -I also. Similarly, we can check for G equals to -J, K and -K. We will get the same element -I for this 4 elements. Okay. That's why the conjugacy class of I, that will have only 2 elements, I and -I. I am erasing this 2. Similarly, we can find the conjugacy class of J and conjugacy class of K. Mm, Okay, so this will be J and -J, and this will be K and -K. Uh, okay, what if we want to find the stabilizers also? So if we don't want to get confused, I'll prefer to write it as CI, CJ, and this is CK. Now, what is a stabilizer of I in Q4? that is Q4I. We can use that notation. This will be if G collection of G belongs to Q4 such that the conjugation G inverse, this will give us I again. Okay, that is G belongs to Q4 such that this will imply that Gi is Ig. Okay, so how many G will be there such that these two will be same? So obviously for G as 1 and minus 1, we will get this. Okay, so the stabilizer will have two elements and the stabilizer will be 1 and minus 1. Okay, similarly, this will be the stabilizer in Q4 for J and for K and like for minus I, minus J and minus K. So now come to class equation. Class equation will be cardinality of G, that will be summation of okay, let's split it. So first term will be order of center and summation x belongs to lambda 1. This will be G by Gx. So we will get this as, sorry, this is it, which is 1 plus 1 plus 2 plus 2 plus 2. Okay. Now, the next question is find conjugate classes and class equation for this. So this is simpler question. Here we have G as Z8 and since Z8 is abelian, center of Z8, that will be Z8 itself. Okay. So the class equation will be reduced in this only. That is 8 will be 1 plus 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 1. So this is 1, 2, 3, 4, 5, 6, 7, 8 times. Okay. So whenever you get a class equation where like you have all ones, so we can conclude that this is a class equation corresponding to the to an abelian group. Now, consider this question. Let G be a group of order Pn where P is a prime and n is a natural number. Then which of the followings are true? So let the order of G is P to the power N. Then we can use the Cauchy's theorem, which says that whenever we have a prime power, and if, okay, let's recall this. If some D divides order of G such that this D is a prime, then there exists an element of G of order P. Okay. It means G has an element of order P. But what about P square? So suppose G is uh, something like Z mod PZ cross Z mod PZ, then what is the order of G? Order of G is P square, but G has no element of order P square. Okay, we can only conclude that G will have an element of order P, but not about P to the power some natural numbers greater than 1. Okay, so the option 1 is false. Second one, all elements have P power. So we know that if G belongs to G, then order of G divides order of capital G. That is the order of any element in a group divides order of the group. Okay. That is order of G divides P to the power N. Now P to the power N where P is a prime. So order of G that can be either P or P square. Let me write it. Or P to the power N. All are powers of P. Thus, all elements of the group G has P power, or we can say that okay, all I'd like to say all non-identity. If we okay, let me clear it out. G is P to the power some I, where this I can be 0, 1 up to n. Okay, so corresponding to this 0, we will have p to the power 0, that is 1. That is, we will have the identity element of the group. And for all, that is I from 1 to n, we will get non-identity elements. Now consider this question. Let G be a group and all non-identity elements of G have the same order. So actually we are assuming here that G is finite. Okay, and that is actually, like, we are using this term, they have the same order. That is, we have some fixed number as the order. We have some natural number. Okay, we are not talking about the infinite order this time. Now, if G is a finite group, that is, if order of G is finite, then order of G will be something like P1 to the power R1, P2 to the power R2, Pk to the power Rk by prime factorization of the order of G, or like by the fundamental theorem of arithmetic. Where Pi's are prime and Ri's are natural numbers. Um, if we take all as natural numbers, we will exclude the possibility for non-trivial trivial group. So, okay, for generality, I'm writing non-negative integers. Okay, now orders of, okay, each non-identity element is same. That is the key actually. So from here, what we can see, uh, P1 divides order of G. So there exists some element of order P1 Similarly, P2 divides order of G. So we will have some element of order P2 in G and so on. Okay, this will contradict this fact that order of each non-identity element is same. Therefore, this prime factorization of order of G will be reduced in power of uh, only one prime. Okay, therefore, this is P to the power R, where R is non-negative integer. For integer 0, this is trivially true that there is no non-identity element. So, like, their orders are same actually. Okay, now what if this is a positive integer? For any G belongs to G, we have order of G divides order of the group, that is order of G divides P to the power R. Therefore, order of G can be P to the power I, where this I can be, or you can write I belongs to 1 to up to R. Okay, 0 can't be this time as we are taking non-identity. That is order of each non-identity element as they share the order is P power. Mm, or directly we can say there must be an element of order P. Therefore, all non-identity elements has the power P. Okay, and we have also checked that order of G is P to the power R, that is order of G is a power of P. Okay, so yeah, we can do this question using Cauchy's theorem. So this is all for today's session. We will discuss some more questions on this topics, group actions and their applications on Stylus theorem in next problem solving session. Thank you.